Okay, a question was asked about question 6.1 and trying to looking at the individual groups that you have to look at for determining whether a double bond is E or Z. So let's just take a look at 6.1 then. So in this question, it asks which alkenes are cis or are EZ isomerism possible. So just indulge me for a moment. What's the difference between EZ and cis trans? So if you have a carbon-carbon double bond where you have a hydrogen and this is a non-hydrogen group. That's what X stands for. If you have a double bond where you have a hydrogen and a non-hydrogen group attached to each of the two carbons, we can use cis-trans to determine or to designate that stereochemistry. And the reason we can do that is because if I asked you if the top molecule is cis or trans, you would say cis. Now, it doesn't matter whether you look at the two non-hydrogen groups or whether you look at the two hydrogen groups. They're both on the same side of the ring, so it doesn't matter what your frame of reference is. And I will just point out that these non-hydrogen groups, they don't have to be the same. So maybe I would make them like X and Y. So it doesn't matter whether you're looking at the non-hydrogen groups or the hydrogen groups, you're going to give me the same answer. You're going to give me cis. Down here, I'll just change this to a Y group. If I said, what is this? You would say trans. And it wouldn't matter whether you were looking at the two hydrogens or whether you were looking at the two non-hydrogen groups. You would get the same answer. So when does E and Z come into play? Well, E and Z comes into play when the minute that you have three non-hydrogen groups, a minimum of three non-hydrogen groups attached to the double bond. Because now I can't say, I don't have the hydrogens as a point of reference to say, oh, well, it's cis or trans. So this is where IUPAC said, if you have, this situation, we're now going to use E and Z, where E stands for the German word Enthagen, which means across, or something close to that. And Z stands for zusammen. I believe these are S's actually. Zusammen, which I know means together. So this is the equivalent of cis, and this is the equivalent of trans. And then they farmed out the project to Cahn, Ingold, and Prelog to then come up with a system to basically compare these two groups and give one a high priority and the other one a lower priority, and do the same thing here. And then we can compare the high priority groups. Are they together, zusammen, Z? Are they trans, Enthagen, across, E? So it's the Cahn-Ingold Prelog sequence, what are called the sequence rules, that we use to determine if, and let me just change this hydrogen to a W. So who has the higher priority, X or W? Who has the higher priority, Y or Z? And then we turn it into a cis-trans-like system. So this question is only asking which alkenes there is an EZ isomerism possible. I will also make one other statement, and that is that whenever you have a double bond where two of the two groups attached to one of the carbons, these groups are the same, then there is no cis-trans, and there is also no E or Z possible in the naming. So if a carbon has the same groups attached to it in the double bond, there's no cis-trans or no EZ isomerism possible. And the whole idea here is that when you have cis or trans, you can change the stereochemistry, you can change the shape by basically interchanging these groups on one of the carbons. So I have a different shape when the hydrogens and non-hydrogen groups are cis than versus whether they're trans. And if I come down here and I have 4 different groups, interchanging the Z and the Y is going to give me a completely different shape than keeping the Y and the Z in the same position. Up here, if you have the same group, interchanging it does nothing. It doesn't change the shape. Okay? So that's my little quick, not so quick, rundown on what cis-trans and what E and Z really mean. So now let's go to problem number 1 here. And if we look at number 1, we have a ring with a carbon-carbon double bond, and over here we have an H and a CH3 group. Now, it doesn't matter whether I put the H on top or the CH3 group on top. Does this molecule have the possibility to be E or Z? And the answer is no, because these two groups, basically, which are attached to these two groups, which then interchange, those two groups are the same. So these are the same groups. So it's like this situation over here. No cis or trans isomerism. Or easy isomerism. So now we go to 2. I've got a carbon-carbon double bond. On this carbon, I've got an H and a CH3. And over here, I have an H and an ethyl group. Is this molecule, does this have the potential to be E and Z? And the answer is yes. Now you could say, but wait, it's cis or trans. It could be cis or trans, yes. So when you have cis or trans, you automatically have E or Z, because hydrogen always has the lowest priority in the Cahn-Ingold Prelog sequence rules. So in this case, yes, this one could be EZ or cis-trans. 1-octene, any time the double bond is at the 1 position, and we would have now the carbons. Those two groups are the same. It is not cis or trans. And finally, if you look at this one, the carbon-carbon double bond, over here I have 2 methyl groups. Over here I have 2 ethyl groups. That's what the C2H5 means, a CH2CH3 group. Same group here, same group here. Not the possibility of E or Z. So only 2 has the possibility of E or Z. Okay. So that's question 6.1. Now, this is from one of the homework problems at the end of chapter 6, the ones that you have just for that you can do for review. They're not graded. But now let's kind of begin to take a look here at isolating and identifying the groups attached to each one of these carbons. So if we look at this molecule, the ultimate question is this E or Z? I have basically, here's my carbon-carbon double bond. I have, and I'm going to go ahead and just use the highlighter for a minute. I have one group here. I have another group attached to that carbon. So I'm going to compare those two. And then over on the other side, I've got this entire group. And I've got this entire group. So I have 4 different groups attached to the carbon-carbon double bond. And so if I'm going to determine E or Z, I need to know the rules for E and Z. So I'm going to basically, I compare these 2 groups and determine which one has the higher priority under the Cahn-Ingold Prelog sequence rules. So I'm going to just write that down here and kind of isolate it so it's clear what I'm doing, maybe. And I'm going to go through the Cahn-Ingold Prelog sequence rules to show you how we would use them. Okay, so the number 1 Cahn-Ingold Prelog sequence rules. Number 1 is that I'm going to look at the atoms that are attached to the carbon of the carbon-carbon double bond. And the one with the highest atomic number wins the high priority. Okay, so that's rule number 1. So looking at this molecule then, I have a carbon and a carbon. So they are tied. On this carbon over here, I might as well I'll do them both at the same time. Over here I have a CH2 attached to another CH2 attached to a C with a triple bond N, and then down here I have a CH2 attached to a CH2 attached to an NH2. And so I'm going to take these just one at a time because that's what I'm comparing. So let me move back to the left one. I have 2 carbons. They are tied. So then we go to rule number 2. Rule number 2 says that we look at, if they're tied, if they have the same atomic number, we look at all the atoms attached to those atoms, and the one with the highest atomic number wins. Okay. So that's rule number 2. So now I'm going to look at the atoms that are attached to this carbon. And what do I have? 2 hydrogens and an oxygen. So I'm already taking into account the fact that both these carbons are attached to the C double bond O. So I'm forgetting about that. So I have 2 H's and an oxygen. Okay. Up here, I have a carbon because it's just attached to this carbon. But I've got a carbon-carbon triple bond, so now I have an issue. Got a huge issue. And the huge issue here is I have 3 atoms versus 1, and that's not a fair battle. So what I need to do is I need to go to the Cahn-Ingold Prelog sequence rules, and I need to figure out how to handle multiple bonds. So I'm going to go to the next slide and show you how we handle multiple bonds. Okay, so here's my C triple bond C group. I need to write what's called an equivalent structure. So in the equivalent structure, what I'm going to do is I'm going to start by only writing the single bonds. And then I'm going to add the multiple number of single bonds. So what I'm going to do is I'm going to replace the multiple bond with a multiple number of single bonds. What does that mean? Let's take a look at this carbon right here. That carbon is attached by a triple bond to another carbon. That means it needs to have 3 CC single bonds. So here's the first, here's a second, here's a third. So I've replaced my CC triple bond with 3 CC single bonds. Okay. And now for this carbon, I now have 3 things attached to it. So now I've got a fair comparison. But it's not just this carbon that I look at. It's this carbon, because this carbon also has a triple bond. So I'm going to say that I'm going to replace this carbon from the red carbon's perspective. I'm going to give it 3 CC single bonds. Well, here's the first one, here's a second, here's a third. So now I've drawn what is called the equivalent structure of the carbon-carbon triple bond. Okay. Now, this has no physical or chemical reality. This is just a game that we play to take a carbon that has one atom attached to it and make it so that it has now 3 atoms attached to it. So that now I can do my comparison. So let me go back here to the original molecule and say, okay, this carbon-carbon triple bond would now have the equivalent of a C with 3 C's attached to it. The other carbon would also have 3 C's attached to it, 1, 2, 3, and then the hydrogen. So this is the equivalent structure that I'm now going to compare down here to this carbon. So the question is, this carbon had 2 H's and an O. What does this carbon have? 3 C's. Okay, I'm going to go back to the equivalent structures in a moment. But now I have a fair comparison. 3 C's versus 2 H's and an O. The rule is that you look at all the atoms, and the one, that means the singular atom that has the highest atomic number wins. Okay? That singular atomic number is O. So O beats H, O beats C, so that means this group then wins the high priority. Okay, so of this yellow group and of this green group, I use a check mark to say the CH2, OCH3, the ME stands for methyl, that group now has the high priority. So now I need to do the blue and the purple to figure out which one of those 2 groups has the highest priority, and to determine then whether the 2 high priority groups are cis-trans, which would translate to Zusammen and Enthagen. Okay? So let's go ahead and do that. So looking at this, the first group here, carbon versus carbon, tie. What's attached to this carbon right here? 2 H's and that C. What's attached to this carbon? 2 H's and that C. They're tied. So now we move on to the next group. What's attached to this carbon? 2 hydrogens and a C. What's attached to this carbon? 2 H's and an N. So now we compare 2 H's and a C versus 2 H's and an N. Is there one atom there that has the highest atomic number? Yes, it's nitrogen. And so now this group wins the high priority. And so the 2 high priority groups are basically cis, which means that geometry is Z. So you keep going until you find a point of difference. Okay. Let's go back to the equivalent structures. So there was on that molecule C triple bond N. So what would be the equivalent structure of the C triple bond N? I would again write just single bonds, and now I'm going to replace the CN triple bond with now 3 CN single bonds. And I'm now going to replace the NC triple bond with 1, 2, 3 NC triple single bonds. So this would be the equivalent structure of a C triple bond N group. So this carbon then, if we were to evaluate it, would have 3 N's attached to it. Again, this has no physical or chemical reality. This is just what Cahn, Ingold, and Prelog came up with in order to have rules in order to handle the multiple bonds as well as then the whole series of sequence rules. Okay. So let me just kind of reiterate this, and we'll do more of this after the exam. But these carbons then are sometimes called, at least they were years ago, they're sometimes called phantom carbons. The phantom carbon terminology came about because many years ago when I taught with Dr. Weaver, who knew more chemistry, or who forgot more chemistry than I will ever know, his students came in and said, can you tell us what phantom carbons are? And I had no idea what phantom carbons were. And I said, well, what are you guys talking? What topics are you talking about? And they said, well, we're doing EZ and RS. And I said, okay, phantom carbons are these carbons that don't exist except when we're using them for equivalent structures. These would be phantom nitrogens. Okay. So the whole idea here is that we use these Cahn, Ingold, Prelog sequence rules in order to judge these two groups as to which one has the higher priority, these two groups which one has the high priority, and then we compare the 2 high priority groups. They will either be cis together, zusammen, Z, or they will be trans, across, entgegen, E. Okay? And so we get more into those. The same sequence rules will be used for chiral centers when we do R and S. So we have to learn this one set of rules to handle both EZ and what is called R and S later on. Okay? So hopefully this gives you just an introduction and the different steps that we use in order to get E and Z, and we'll go into much more of this after Monday's exam.